divisible goods and indivisible goods. Good is divisible if you can share it into subparts. For example, in this example, what are the divisible and what are the indivisible goods? What about the bank account? Is it divisible or not? It is divisible. What about the children? Actually, they are divisible as well. I mean, the time spent with the children is divisible. This is what counts. Otherwise, if they were not divisible, there would not be shared custody. And of course, I mean, the stereo and cats are most probably indivisible. Then something very different is, imagine a jury in a trial, in court, and they have to agree on a verdict. They have to decide whether the person who is convicted is really committed a crime and how many years of jail she should get. So this is also a common decision making. They have to agree on the verdict. And the last example, which is quite different, is about when you have different search engines that give several rankings for a given query, then we have to aggregate these rankings given by the different search engines. If we look at these examples, actually we can maybe make a classification between two big classes. If you consider the first four, against the last two, can you see a big difference between these four and the last two? So if I draw a line here, can you see a big difference? About what? If I tell you that there is a big difference, it means that there is a big difference. But what is it about? It's not anything technical. It's something about the nature of what we process, the nature of data. What are we speaking about in the first four cases? Making a decision, but also there we are making a decision. Maybe well, the last case is maybe not clear, but this case we are making a decision. So it's something more specific than that. Yes?
The outcome of the first four doesn't affect the voters.
So the outcome of the first four does not
affect the voters.
Okay, does not affect the voters. Okay, so we're going there. Yes. So that's true. That's very true. You mean okay? The outcome of the first four affects the voters, and the last two does not affect. Yeah. Okay. So that's it. Actually, in the first four examples, voters express preferences. They express really their own preferences about the final state. They will be affected by the final state, and they have preferences about it. In the last two cases, if you take that one, the juries they are not really concerned by how many years of jail the convicted person will get. They just want to agree about the truth, but they don't express preferences. And it is even more clear here. Actually, search engines do not have any preferences. They just try to give what they believe to be the truth. They try to give you the web pages that they believe to be the most relevant, but they don't have any preferences. They are not concerned by the decision. Okay? Is it clear for everyone? And this is an important distinction. This is an important distinction between these two classes, because when it comes to talking about strategic behavior, which is like voters or agents not telling the truth about their true preferences, this will have an impact in examples of these types, but not, or probably much less for these types. Okay, so let's go a little bit more technical. So let's define social choice theory as a very general framework, and then we will move slightly towards voting, which is more specific. So in social choice theory, we have a set of agents, a finite set of agents. So we will always use n for the number of agents. We have a set of alternatives, x, which generally is finite as well. Then each agent I has preferences over the alternative. So I'm going to restrict on those examples where the agents are concerned by the decision and they have preferences. So each agent has preferences over the alternatives. And the goal is to choose a socially preferred alternative. So an alternative for the society, and that tries to be as consensual and as fair as possible. Then there are two important subdomains of social choice. Actually three. This is actually three important subdomains of social choice. So the first one, which will be the topic of the course, is voting. So in voting, agents are usually called voters, and they express their preferences over a set of alternatives that we sometimes call candidates, not always. And they must come to choose one candidate or sometimes a subset of candidates. Then another important subdomain of social choice is fair division. So fair division, remember the example of the divorce settlement. So this is a fair division problem. Then we have agents who express their preferences about combinations of goods that they may receive. And the outcome should be an allocation of goods to agents. The allocation, the final allocation should say this good goes to that agent, this good to that agent, and maybe this good is shared between these agents. And a third class of social choice problem is judgment aggregation. So remember the example with the jury that has to agree on the verdict. So in judgment aggregation, agents or juries express their opinion about the truth of each of a number of propositions, and one must come up with a common assignment of truth values to each of the propositions. So the propositions could be, in the examples of the verdict, the propositions could be: is the person guilty? Was the person responsible for what he or she did? And should the person go to jail? Okay, so these are a number of propositions, and they have to agree on a value for each of the propositions. Okay, so that was. So most of the talk will focus on both. So I said that every agent expresses some preferences over the possible alternatives. So what does it mean, preferences? So it may mean different mathematical objects. So sometimes we use cardinal preferences, which means that each agent evaluates each alternative with a number. Okay, so we have we say that we have a utility function that maps every alternative that for each agent maps every alternative of x to a real number. Or sometimes we don't want to use numbers, but we use labels from a qualitative scale, such as excellent, very good, good, average. If some of you have used TripAdvisor, for instance, TripAdvisor uses real numbers. Do some of you use TripAdvisor or tools like that? Okay. But there are other tools that use linguistic evaluations, actually, qualitative labels. And if some of you, for instance, have reviewed papers for conferences, and some conference management systems use qualitative evaluations, such as strong accept, accept, weak acceptance. Okay, so second type of preferences, which will be more central to the talk, is ordinal preferences. So when agents express ordinal preferences, they don't give numerical evaluations to the alternatives. They give a ranking, or sometimes a partial ranking. So they just say, I prefer, so my preferred alternative is that one, and then that one, that one, that one. Okay, so they rank the alternatives. Sometimes we may allow ties between alternatives, sometimes we don't. And the third kind of preferences, which is probably the simplest kind of preferences, is dichotomous preferences, where each agent just partitions the set of alternatives between good and bad alternatives. For doodle poles, it's a little bit like that. Doodle poles, at least the basic version of doodle, for each of the alternatives, the agent would tick yes or no. Yes, I can. No, I can't. Right? Of course, in the end, there are more sophisticated uses of doodle where you can also question marks. But the basic version of doodle is about dichotomous preferences. Okay, so there are also more sophisticated preference models, but I don't want to talk about that. Okay. So now, in short, let me, in a few minutes, let me talk a little bit about the history of social choice and the role of computer science in it. So, as I said already, so at the end of the 18th century, we got the first formalizations of collective decision-making problems, namely with the big names of Condorcet and Borda, which we will, these names we will encounter them again and again during the talk. And then, the beginning of the 50s or the 1950s, then there was a breakthrough in the formalization of collective decision-making problems with so it became really a subfield of, for some reason it became a subfield of economics, but also maybe a subfield of mathematics. And so the main, actually the result that is considered to be the birth of modern social choice is Arrow's theorem, which I will talk about in a few minutes. And at that time, so the results that these mathematicians and economists were looking for are what we generally call impossibility results, such that an impossibility result, we'll see one in a few minutes, but as typically that form. There exists no way of aggregating preferences satisfying this property and that property. Okay, so this is a negative result, which means that if you require a few intuitively desirable properties, then you get the answer that this is not possible to jointly satisfy these properties. More positive class of results is characterization theorems, where so a theorem of that kind says, if we want a voting rule, say, to satisfy this and that property, it has to be a voting rule of that class. Okay. But these theorems did not really speak about how to compute the outcome. So computational issues were neglected. And then the third period is from the early 1990s, and even more since the early 2000s. Then computer science comes into play, and that was the birth of a new discipline called computational social choice, where researchers come both from computer science and economics, a little bit more from computer science. And the subfields of computer science that are important, the key topics are AI, computation systems, but also theoretical computer science, operations research, a little bit of databases, and also machine learning. And the goal of that, why does computer science come into play? It's because the many problems in social choice are intrinsically difficult, computationally difficult, we see why. And then computer scientists can bring the method, the notions and the techniques to help solving these problems. This may look a little bit abstract, but we see examples. But most of the tutorial will be about examples. Okay. So that was the first part. So now I'm going to talk a little bit more about social choice theory, and I will give Arrow's theorem because you can't go out of the room without knowing Arrow's theorem, and then we'll go quickly to more practical things. Okay. So from now on, we'll focus on voting. So we won't talk about social choice we won't talk about the general picture of social choice, but we focus on voting, which is a subtopic of social choice. Voting and preference aggregation. So I need a few definitions. So again, we have a finite set of voters. Okay. We also have a finite set of candidates or alternatives, and a profile consists of a preference relation for each voter. And well, in voting, the classical model for preferences is ordinal preferences. So in most cases, not all, I will give a few examples of exceptions, but in most of the time we ask voter to rank alternatives, to rank candidates, and not to give valuations to candidates. So under this assumption, so each voter gives a ranking. So this is the ranking of voter 1, this is the ranking of voter n. Okay. Sometimes I also use V1, vote number 1, vote number n. And the profile P is a collection, is a tuple of such votes, of such rankings. And yeah, so P is the set of profiles, P is the set of rankings, and P or n is the set of all profiles. And then a voting rule, or sometimes called a social choice rule, is a function or that maps every profile to a single candidate. Okay, so it's a function that takes a profile and that outputs a winner. A social choice or a voting correspondence is almost the same thing, except that the input is the same, but the output is a little bit different. We don't have to output a single winner. We output a subset of what we call co-winners. And this is very useful when we have ties. And the example comes just after. And sometimes we need a little bit more. We need to output not only a winner or a set of co-winners, but we need to output a ranking. We need a collective ranking. So we take some rankings, a ranking for each of the voters, and we want to output the ranking. So this is what we call an aggregation function. Okay, so I said that sometimes we need to work with these correspondences instead of rules because of ties. So why do we need correspondences? It's because, suppose that in the simplest case, suppose that we have only two candidates. So I use M, I will always use M for the number of candidates. Okay. N is the number of voters, M is the number of candidates. Okay. Suppose that we have two candidates, A and B. Okay. So in that case, I think that we would agree that the obvious choice for making a decision is majority. Majority says if more voters prefer A to B than B to A, then choose A and vice versa. The problem is about when exactly half of the voters prefer A to B and half of the voters prefer B to A. If we want, so if we have a voting correspondence where we can output a set of candidates, then that is not a problem. If we have a perfect tie, we output AB. Okay, so the voting correspondence says, okay, there is a perfect tie between A and B, and the output is AB. The decision has to be made by some other trick. This is, and we'll talk about that in the next slide. If we want a voting rule, on the other hand, so a voting rule must output a single candidate, okay, a single winner, and if you have a perfect tie, then there is a problem, because I mean we have to make a decision between A and B, even if there is a perfect tie. So the first, and there are two basic ways of doing that. I mean, the first, probably the most classical way, is to give up neutrality. Neutrality is the property of a voting rule that says that all candidates are treated equally. Okay? If we give up neutrality, it means that we may have a priority relation over candidates, and in case of a tie, we give, I mean, the winner is the candidate that has the highest priority among those who are tied. Okay? But sometimes we can also use another way of breaking ties by giving up anonymity. Anonymity is the property of voting rules that say that all voters count the same. If we break up anonymity, we may have that in case of a tie, the head of the committee decides. Actually, I was a few days ago, I was in the committee for selecting a best paper, and it was a small committee, and we got to a tie, and then the head of the committee said, okay, I voted for this paper, so this is the winner. And he had the right to do that. Do you have, I mean, so if you define an election system, if you define a political election system, there needs to something to be said about ties. And there needs to be, in the constitution of the country, when talking about election systems, there needs, I mean, the constitution should specify what to do in case of a tie. Right?